All right, our final speaker in this session is going to be Jun Yun from the National University of Singapore, where he's doing his PhD. And we are going to now add in GANs to the eclectic mix of MLAI MPC we've had going on today. And specifically, we're going to see a variant of the work focusing primarily on vertically partitioned data.
Okay, and I am Yuan Xun, and this work is cooperated with Mr. Yang sitting there, and Dr. Ayan, and this work is supervised by Dr. Prasanna Gop from University of Sheffield and Professor Biplab Sikda from National University of Singapore. And in this presentation, I will present our work VFLGAN, a vertical federated learning-based generative adversarial network for vertically partitioned data publication. And in this presentation, I will take you through the background, problem formulation and research gap, and the proposed VFLGAN, and experimental results of VFLGAN. And last, I give a privacy analysis of the synthetic data sets. First, I will introduce the background. AI is an emerging technology, and current AI models are data-driven and highly depend on the training data. However, sharing personal data directly is prohibited due to the privacy regulations. And to protect privacy, we can release a synthetic data set for AI purpose. And for example, the cars in the figure are generated by DALL-E, and you see they are high quality and can be used for training an AI model. However, in vertically partitioned scenarios, the attributes of the same users are distributed in different parties. And the data cannot be shared across different parties due to the privacy concerns. And the target of the vertically partitioned data publication is to release a synthetic data set that contains all the attributes from all the parties and without sharing their local data. And for this problem, we have three assumptions here. The first is there are n users in party 1 and party 2, and they are same and can be aligned. And the second, party 1 and party 2 contain different attributes. And the third is the local parties and the central server are honest but curious and non-conclusion. And the problem can be formulated as the following. There are m parties, and each party maintains a private dataset, and the m private datasets can be combined to construct a new dataset X. And we aim to generate a synthetic dataset X tilde, where for the samples in X tilde should have a similar distribution to the samples in X. And if we train a normal GAN, for example, WGAN GP in each local party, then we can generate local synthetic data and which has a similar distribution to the local private data. However, the research gap is that the Formula 1 doesn't mean the combination of the local synthetic data to have a similar distribution to the combination of the local private data. And now I introduce the proposed system that solves this problem. And in this system model, the server maintains a shared discriminator, which is the key point to learn the correlations between the attributes across different parties. And in each local party, there is a private dataset Xi and a private generator and a private discriminator. And in the training process, the local party transmits the intermediate features of the local discriminator to the server. And then the server returns the gradients back to the local party to optimize the local discriminator and local generator. And in the inference process, each local party generates a local synthetic data and transmits it to the server. And last, the server combines all the local synthetic data sets to construct X tilde and then release it to the public. And our system model has two objectives. In objectives 1, we want the combination of local synthetic data sets to have a similar distribution to the combination of local private data set. And this is also the objectives of the vertically partitioned data publication. However, when the attribute set is large, the objective 1 is not enough, and we need objective 2 to enhance the quality of synthetic data sets. And in objective 2, we want the local synthetic data set to have a similar distribution to the local private data set. And this is the training objectives of our system model. And the objectives 1 is achieved by optimizing the discriminators and the generators according to the loss functions from the shared discriminator. And the objective 2 is achieved by optimizing the local discriminators and local generators according to the loss functions of the local discriminators. And we also construct a baseline named VFLGAN base by deleting the two loss functions from the local discriminators to evaluate the effectiveness of the objectives 2. And this figure shows the overview of the VFLGAN for two-party case, and we can see that the system is optimized according to the loss functions from the local discriminators LD1 and LD2, and also the loss functions from the shared discriminator LDS. And this figure shows the overview of VFLGAN base, and the system is optimized according to the only loss functions of the shared discriminator. And for evaluation, we use one image data set with a large attribute set, and 3 tabular data sets with a small attribute set. And we also use 2 baselines. The first one is WGAN GP, that is trained in a centralized manner and serves as upper performance limit for the vertically partitioned scenarios. And the second is VFLGAN, which integrates horizontal federated learning and GANs for vertically partitioned scenarios. And this figure shows the results on the image data set. And we can see that WGAN GP shows the best performance since it trained in a centralized manner, and followed by VFLGAN, VFLGAN base, and VFLGAN in sequence. And we can see the performance order is the same under the 2 evaluation metrics. And for tabular data sets, we can see WGAN GP, VFLGAN, and VFLGAN base show a similar performance and outperforms VFLGAN. And we can have the following conclusions from the evaluation results. First, the performance of VFLGAN and VFLGAN base is close to that of WGAN GP and better than VFLGAN, which shows the effectiveness of the proposed framework. And second is for a large attribute set, for example, the MNIST set, the VFLGAN outperforms VFLGAN base by a notable margin, while for a small attribute set, they show a similar performance. And this can be explained. The information loss in the shared discriminator is negligible for a small attribute set. However, when the attribute set become larger, the information loss become significant, and we need local discriminators to improve the quality of the synthetic data. And also to further protect privacy, we apply a Gaussian mechanism to make VFLGAN satisfy an epsilon delta dp. And the differentially private VFLGAN also present a reasonable performance. However, as pointed out in reference 3, the synthetic datasets are not safe from privacy attacks. And for privacy auditing, we combine shadow model attack with leave one out assumption, which is a stronger assumption than that in reference 3. And we use the attack performance to estimate the potential privacy breaches through the synthetic datasets. And this table compares our auditing scheme with other membership inference attacks. And due to the strong assumptions of our scheme, the AUC performance of our auditing scheme is much higher than the membership inference attack with realistic assumptions. And this table shows the AUC performance of our auditing scheme on the synthetic datasets generated by VFLGAN and differentially private VFLGAN. And from the table, we can see that the privacy breaches of VFLGAN is not significant. And after applying DP mechanism, the privacy breaches become negligible. And we have following conclusions in our paper. First, we propose VFLGAN for vertically partitioned data publication, and then we provide an auditing scheme that applies membership inference attacks to estimate the potential privacy breaches. And also, we integrate a Gaussian mechanism in the training process of VFLGAN to make it satisfy differential privacy. And the privacy breaches through the differentially private VFLGAN is less than that through the VFLGAN. And thanks for listening. Feel free to ask any questions.
Hi, thank you for the interesting talk and work. For me, it is not clear how you kind of train the discriminator on the server, and is this some sort of intermediate leakage? Because to train the discriminator, maybe you have to send.
I see.
Yeah.
I see. You mean there should be some potential privacy breaches from the features and gradients in the transmission process.
Yeah.
And
correct.
actually, in our paper, we evaluate. We also apply a membership inference attack to evaluate the potential privacy breaches of the features transmitted to the server. And the result shows that even for the non-DP method, the privacy breaches is minimal for our auditing scheme. Maybe,
yeah, but I'm more concerned maybe with, for instance, model inversion that would allow you to kind of reconstruct the original data rather than membership inference.
Yeah, but as we know, the inverse attack is more difficult than the membership inference attack. Mm. So if this framework is safe from membership inference attack, then it's very difficult to launch a inverse attack successfully. Yeah, okay. That's the logic.
Thank you.
Sorry, I didn't notice in your experiment if you show that if they train simply locally their data and then they publish it, it's less accurate or less private. You had in your experiment just because they have separate features, if they just train locally GAN on their own data set, and then they publish the new synthetic data set locally, so I have D1 prime, D2 prime, Dn prime, and then combine them.
Yes.
You have any comparison of that one? What happens if...
No. I didn't I didn't compare for the WGAN GP trained only in the local party.
Yeah, because it's vertically. I was thinking maybe it's not that much worse, but yeah, maybe
Yeah,
future
because-
direction.
Yeah, because in my perspective, that doesn't work. Theoretically, that doesn't work.
No?
Yeah.
Okay, thank you.
All right, let's thank the speaker one last time.